All right, trust you did well on that quiz, and certainly I'll get back to you on your quizzes for those who watched on YouTube. And go and have your homework out if you would, please. Books open to page 128. You had 6 questions to answer. Questions 1, 4, 5, 6, 8, and 9. So 1, 4, 5, 6, 8, 9. Starting a new section here. We've been talking about motion. What happens, right? And we looked at vectors, and we looked at velocity and acceleration. We looked at vectors being collinear. We looked at them being perpendicular, skewed. Then we broke them into components. But none of this has explained why the motion takes place in the first place, right? Why is Kendall falling from a ledge? We don't know. Let's explore, okay? And so she actually made it back from the mountains in one piece. So one small piece. Anyway, all right. So page 128, questions 1, 4, 5, 6, 8, and 9. And let's take a look. Number 1, define Newton's first law of motion. Michael.
Newton's first law of motion describes inertia and says that things in motion tend to stay in motion and things at rest tend to stay at rest.
Okay, what did you have, Audrey? Maybe expound just a wee bit more.
Newton's first law of motion states that a body in motion tends to move in a straight line at a constant speed, and a body at rest tends to stay at rest unless acted upon by an outside force.
Good, and that's kind of the kicker, is unless acted upon by an outside force, yes, bodies will maintain their velocities. If their velocity is 0, it'll maintain a 0 velocity. If the velocity is whatever, well, that implies straight line, same direction, same speed. So velocity would remain constant except for some outside force intervening. So question number 4, what are 2 alternative definitions of Newton's first law? Give me one of your answers for number 4, Michael.
Everything's current velocity is constant.
Good, I kind of actually just alluded to that. And the other way that we could define Newton's first law.
I said the body can't accelerate except under the influence of a force.
Good, a body will not accelerate then. Again, if velocity doesn't change, except in the presence of a force, what do we call a change in velocity? Acceleration. A body will not accelerate without some external force present. So between the 3 of those ways of phrasing, it helps, I think, to give us a very complete view of the first law of motion. Number 5 says, what is the equation for Newton's second law of motion? And letter B, how is force related to mass and acceleration? Letter A, Audrey, give us the equation.
The equation is F equals M over A times A.
Good. F equals M times A. And then letter B, how is force related to mass and acceleration, Michael?
It is directly related to mass and acceleration.
Directly proportional to both. Good. Number 6, what are the units for force, mass, and acceleration, and how are these units related? Let's take them one at a time, class. What's our unit for force?
Newtons.
What's our unit for mass, class?
Grams, kilograms.
Kilogram, remember? And then for acceleration,
Meters per second squared.
and the question is, how are these units related? Well, going all the way back to the previous chapter, they refreshed your memory here. What is a Newton, Audrey? This was the second part of the answer, Michael.
It's about 4 pounds.
Yeah, well, no, but it says, how are these units related? A Newton is a kilogram times meter per second squared, and that's how they're all related together. So anyway, maybe jot that down there in your homework or in your textbook next to number 6. A Newton is a kilogram times meter per second squared. So that's how the units are related to each other. Numero 8. What is the relationship between mass and weight, Michael?
Weight is an object's mass that is pulled by gravity.
Good, we could say weight is the pull of gravity on an object's mass. There we go. More mass, obviously gravity is going to be able to pull more because there's more mass to pull, right? More of you for Earth's gravity to love. Anyway, number 9, what is Newton's third law of motion, Audrey?
Newton's third law of motion has 3 important rules, but it explains equal and opposite reactions.
Okay, there we go. Okay, explains equal and opposite reaction. So for every force, Michael, what did you write?
Every action has an opposite and equal reaction.
There we go. Every action force has an equal and opposite reaction force. Good. Go and set that aside if you would, please. Next section in your in your notes. Yeah.
Was it the Viking voice?
I don't know what that was. All right, Newton's 3 laws of motion. Next section in your notes. Newton's 3 laws of motion. And again, everything we've done thus far has been kinematic. What is happening? What is the motion? We're going to go dynamic here and explain the causes of the motion. That's what Newton sought to do. It all started with the apple, right? Why did that apple fall down? For that matter, why do all things fall down? If I jump up, I come back down. If I trip, I fall on my face. I always fall down. I never fall up. Nothing ever falls up. Why? And hence we credit Newton with discovering gravity. He thought this was a really serious matter, and so called it gravity. And he was always interested in the why. Kendall lays there in her bed. If nothing is done, Kendall will remain in her bed. Why? If Michael is running down the soccer field and somebody steps right in front of him, Michael has a hard time stopping. Why? Okay, all of these different things. If I shove Kendall, I wouldn't really shove Kendall, for the record. We don't support violence against women. So if I shove Kendall, she goes really far. If I shove Michael, he doesn't budge very much. Why? All these why questions, that's what Newton was all about. The whys and the wherefores. And that's what Newton's 3 laws of motion are. So first, law of motion. We call the law of inertia. We've talked about it already, so I'm not going to spend a great deal of time here, except that now that we've defined velocity, we can state it, the law of inertia, this way. An object will retain its velocity unless an outside force affects it. An object will retain its velocity in the absence of an external force. An object will retain its velocity in the absence of an external force. Again, before we said an object will continue moving at a straight line at a constant speed. Well, straight line at a constant speed would be velocity, wouldn't it? So we can shorten the definition of inertia just a little bit there. Well, as I believe it was Audrey in the second restatement that indicated this, that means that in the presence of an external force, if there's an outside force present, external force causes an acceleration, a change in motion, right? And that's the second law. The second law deals with acceleration. Let's talk a little bit about this. Acceleration. What would cause a greater acceleration? For instance, if there's a couple of boxes sitting on the floor, they're just sitting there, their velocity would be 0. Well, if I want to cause one box to move a little bit, I push a little bit. If I want the other box to move all the way to the wall, I shove it harder, right? I mean, that's pretty basic. But more force applied, if they were the same size boxes, same mass, same weight, all of that, more force is going to produce more acceleration, correct? So that we could say that acceleration is proportional to force. Acceleration is proportional to force. But I alluded to it just a moment ago. If one box has stuffed animals in it, and one box has blocks in it, again, thinking of kids' boxes, okay? Stuffed animals, give it a shove, it'll go further. Box of blocks, give it a shove. Oh, that doesn't have stuffed animals, and the box doesn't move as far if the force were the same, correct? If the mass of an object is greater, you will not get the same amount of acceleration, will you, with equal forces. So we could also say that acceleration is inversely proportional to mass. Acceleration is directly proportional to force, but inversely proportional to mass. Okay, now let's think about it from the perspective of the force. How much force do I have to apply to an object? Well, number one, it depends on how much acceleration I want to give it, right? If I want to give it a lot of acceleration, I got to give it more force. If I don't want to give as much acceleration, I don't need as much force, right? If it has more mass, I need to give it more force. Period, full stop, right? So force, then, you could say, is proportional to mass and acceleration. Therefore, F equals ma. And this equation, in a nutshell, is the second law of motion. F equals ma. That is the second law of motion. The force that must be applied to an object is proportional to both the mass of the object and the desired acceleration. F equals ma. Now, we can extrapolate some other things from this. For instance, for Earth exerts a force upon you, right? On some of us, it exerts a stronger force. On some of us, Earth doesn't feel as attached. It's just, the way it is, right? Earth pulls with a certain amount of force, but we know the acceleration of an object as Earth pulls on it, correct? 9.80 meters per second squared, times the mass would give us the force that Earth pulls. We could say that we call this force weight, and weight then equals mass times gravity. We've actually alluded to that already before, but go and get that in your notes again. And there's our definition of weight. I believe we had this back in chapter 1 as well, or back chapter 2 rather, but weight is simply the pull of gravity on an object's mass. The pull of gravity on an object's mass. So again, this is the subtle difference between mass and weight. Mass is how much of you is there. Weight is how strongly does Earth's gravity pull on you, right? So, for instance, you go to the top of a mountain, gravity is going to be weaker up there, right? You will not weigh as much, and that's something we alluded to back in chapter 2. Questions on that? Do you see that this is the same equation? It still is F equals ma. It's just if we're talking about weight, we already know the acceleration, what it's going to be. Assuming we're here on planet Earth, of course. I mean, if you're watching up in the International Space Station, please give me a shout out. That'd be awesome to know. But assuming no one is watching on the International Space Station, I don't believe we have anybody colonizing on the moon or Mars at this point, we know the gravity is pulling on you. The other thought is this. What if we have a couple different objects and we apply a couple different forces, get a couple different accelerations, right? Or what have you. We could make a comparison here as well, make a proportion. That force applied to one object is to the force applied to the other object as the mass and acceleration of the first object is to the mass and acceleration of the second object. And here we can make comparisons between different objects as well. It's not a new equation. It's F equals ma set in proportion or set in ratio, I guess, to another F equals ma is all. We could use this to say, okay, let's suppose it's Kendall. Apply this force, she accelerates this much. I don't know why. We're just happy to have you back. Apply this much force, you get this acceleration. Or we have two different masses. We apply same force to both of you. Well, this mass will accelerate this much. That mass will accelerate a different amount. Okay? Or we've got two different accelerations we're shooting for. And, well, we already did that. We got consistent acceleration, right? Well, if we want the same acceleration, we've got one force required for this mass. For that mass over there, it's going to be different acceleration. Or different force needed to get the same acceleration. All right, questions on all this? Let's pause here on the second law. We'll get back to the third law. Turn to page 112. And you looked at some example problems in your homework reading. I want to go over those with you now. Look at the first example there on page 112, example 8.1, and read it if you would, Audrey.
A force of 5.0 newtons is applied to a mass on a frictionless surface. What is the acceleration of the masses 2.0 kilograms, 5.0 kilograms, or 20 kilograms?
All right, so we've got a specific set amount of force. We have a set amount of mass. And we're wanting, or assuming a variable amount of mass. And the question is, what will be the acceleration if the mass is this, this, or this? So, I don't know, maybe we've got, you know, in the science STEM projects, you have to devise little contraptions that'll always do the same thing every time. Maybe it's a rubber band launcher or something. You've got a nice strong rubber band, and you always pull it back to this mark, and we've calculated that when you release the rubber band, when it hits, it's going to leave a force of 5 newtons. Whatever, that'd be a really crazy strong rubber band. As you put a 2 kilogram object in front of it on a frictionless surface, maybe an air hockey table, for instance, so friction's not an issue, right? It's practically levitating, and pop with the rubber band, it'll accelerate a certain amount. You bring out the 5 kilogram object, don't break the table, It's definitely not levitating, but whatever. Really powerful air hockey table is extreme air hockey, okay? Pull back your extreme rubber band launcher, slingshot, pop, and it launches, okay? And then we take a 20 kilogram object, that's about 45 pounds, crash the table, but it's an extreme table so we can handle it. Pull back your slingshot rubber band, it hits it, and it like barely budges, okay, because it's so big. That's what we're shooting for here. So, we know the force, we know the mass, we need the acceleration. What equation relates force, mass, and acceleration? Class? F equals ma. But if I'm solving for the A, how will I rework it? A equals F over m. So I take the force of 5 newtons, I divide by the mass of 2 kugas, and what do I get for the acceleration, class? 2.5. I said 5 divided by 2, 2.5. And notice, when you divide a newton, which is a kilogram times meter per second squared, the kilograms and kilograms cancel, and that's where you get meters per second squared. I prefer not to think that through. I just prefer to memorize accelerations, always meters per second squared, and we should already have that memorized. Then we say, okay, let's up the ante now. It is now a 5 kilogram object. How quickly will 5 kilogram object accelerate, class? 1.0 meter per second squared. Assuming it was 2 sig figs, right? Yeah, it was. I just was too lazy to put the point zeros. And then we say, okay, now it is a 20 kilogram object. How quickly will it accelerate? 5/20 becomes 1/4, which is 0.25 meters per second squared. Notice that if the force stays the same, acceleration's inversely proportional to mass. As you increase the mass, you are decreasing the acceleration. Questions on example 8.1? We'll look at example 8.2 and read that for us if you would. Kendall.
If a force of 2 newtons accelerates a mass at a rate of 1.74 meters per second squared, how rapidly will the same mass be accelerated by a force of 4.4 newtons?
Do you see here we have 2 different forces? We're looking for a second acceleration and we have 1 mass. Do you see that? So since there's 2 forces and 2 accelerations, we're going to go with this equation. Except it's the same mass both times. It's not a different mass. And if it's the same mass, thoughts? Cancel. So essentially all we're left with is force is to force as acceleration is to acceleration. Make sense? So the first force, it was what, Kendall?
2 newtons.
2 newtons. And the next force was?
4.4 newtons.
When 2 newtons were applied, the acceleration was?
1.74 meters.
And it wants to know what would be the acceleration if 4.4 newtons was applied. All we have to do, class, is? Cross multiply. Start with the 4.4 times the 1.74 and divide out the 2. And what is going to be our acceleration, class?
3.8.
And 2 sig figs, right? Yeah, 2 sig figs gives us 3.8. And acceleration in? There we go. Questions on that? All right, example 8.3. Read that for us if you would, Michael.
An identical force is applied to 2 objects of different mass. One object has a mass of 2 kilograms and undergoes a uniform acceleration of 6 meters per second squared. The second object has a mass of 4 kilograms. What is its acceleration? Assume no friction.
All right, so here I have 2 different masses, 2 different accelerations, same force. Guess what equation we're going to use? That one again. But this time, it's not the masses that match and the masses that cancel, class. What did they say is going to be the same this time? The identical force. So force 1 and force 2 are the same. They're both just force 1. So what can I do with the forces? Cancel. What's left on the left? A 1. Or 1 over 1. And if you were to cross multiply, your equation would be what? Yeah, M1A1 equals M2A2. Here's another way to look at it. If the forces are identical, force 1 equals force 2, right? Well, what is force? Mass times acceleration. So if force 1 equals force 2, then M1A1 equals M2A2. So you can either think of the proportion cross multiplying to get this, or you can think of just substituting an MA for a force. Make sense? So it says the first mass was what, Michael?
2 kilograms.
2 kugas. And did they give you that acceleration?
6 meters per second squared.
And it says the next mass was
4 kilograms.
4 kugas, and we wanted to know the acceleration. Well, we could do this in our head. What's the MA right here, class? 12 newtons. Divide out the 4, we get 3. So that's our acceleration is
3 meters per second squared.
how many sig figs? 3.0 meters per second squared. Okay, questions on that? Seem pretty easy? Pretty basic math there on those. Look across the page, page 113. Page 113, read that example for us now. Audrey.
A car has a weight of 7.3 newtons. What is the mass? Neglecting for what force is needed to give the car a horizontal acceleration of 5.2 meters per second squared.
All right. So it gives me the weight of the car, and it asks for the mass of the car. Class, what equation relates mass and weight? F sub W equals mg, right? Weight is what? Mass times gravity. So I know the weight, I want the mass. How would I get the mass by itself, class? Divide away the gravity, right? So we could say that mass is weight divided by gravity. Now, 7e3, that just means 7,000 Newton weight for the car. Gravity will assume, unless it specifies otherwise, which it doesn't.
9.0.
What is the mass of this car?
7.14 or 714.28 class.
All right, go and put that in the memory of your calculator. So the first question was, what is the weight? What is its mass? How many sig figs? 3 sig figs. So the question is, what is its mass? The first answer we'll round off to the 3 sig figs class is
700.
kilograms. There we go, 714 kilograms. There's our first answer. We're going to use the memory value, though, to get the second thing, which it says, what force is needed to accelerate the car horizontally? 5.20 meters per second squared. So I know the mass. I now know the acceleration that we want horizontally is 5.20 meters per second squared. It says, what's the force? Well, what equation do I use to find force if I know mass and acceleration, class?
Equals
So just take what's on the calculator or in your memory value, multiply by the, fact checking, 5.20 meters per second squared. And how much force is going to be needed here?
3,748.28.
Round it off to 3 sig figs again.
3,710
Of force. All right, questions on this? Seem pretty straightforward? Let's talk about the third law now. Questions at all on the math before we move on? Feel like we've got, okay, third law of motion. And this one is kind of interesting because it's not something we always think about. But Newton's third law of motion says this. For every action force, or for every force applied to an object, there's an equal and opposite reaction force. For every force applied to an object, or I should say an object that does not move, there's an equal and opposite reaction force. For every force applied to an object, there's an equal and opposite reaction force. Unless, of course, the thing moves. Then, of course, it's not able to provide that. But barring movement on the part of the other object, you get an action-reaction force. That's the third law. Action and reaction forces. They are equal and they are opposite. Now, let me give you some examples here. The kids in PE class have questioned about this. Push-ups. We call them push-ups, right? But think about it. What are your arms doing? Going like that, correct? If I go like this, am I pushing toward or away from me, right? I'm pushing which direction? If I'm facing this way, I'm pushing right or left, class? Right. I'm pushing right. Now if I come over to the wall here, sorry YouTube, and I push, which direction am I about to push? To the right. But the wall doesn't move. I move. Why? The wall pushed back on me. Now, if I push just a little bit on this wall, it pushes a little bit back on me. If I really shove the wall, it shoves back on me. Think about it. Imagine you were somehow balanced over water and you pushed down. Your hands would just go down into the water, wouldn't they? Water isn't able to push back up on you the same way, but the ground can, right? You push down on the ground pushes back up on you. You ain't doing nothing. It's the ground doing the work. You act like you're tired after doing push-ups. Really, they're push-downs, aren't they? And the ground pushes you up. Think about pull-ups, right? Bar hanging up there, grab the bar, and what direction am I pulling right now, class? What direction am I going? Down. But the bar doesn't go down, right? I pull down on the bar actually pulls up on you. Unless it's broken. Ever tried to do pull-ups from a broken bar? Or maybe one of those hang over the doorway and somebody didn't secure it properly, you go to grab, whoa! You pulled down all right. You were expecting the bar to pull back up on you, weren't you? But it didn't do that. They're pull downs. The bar pulls up on you. Whoa. Think about just walking. When you walk, what direction are your feet moving? Backward. My foot's going backward, right? Why do I go forward? Because as I push backward, the ground pushes forward on me. So I go forward. Try doing it on ice, right? Foot slips, wet linoleum in the kitchen, foot slips. If the ground doesn't push back on you, boom, down you go, right? Because you slide your foot out from under. Cleats in soccer are helpful because they help to grab the ground. They help the ground to give maximum push forward on you. But really all you're doing is moving your feet backward. The ground is pushing you forward. Think about tires on a car. When they spin, what direction are they spinning? Backward to make the car go forward. It's the ground that pushes the car forward. It's the friction between the tire and the road. Wheel pushes backward, ground pushes forward, car goes forward. The harder the tires push back, the harder the ground pushes forward. Action, reaction. Right? If I slap this desk really hard, okay? Now, I slapped which direction? That way, right? And if it had been a really flimsy desk, the desk just breaks. Fortunately, it's not. But what happens is my hand hurts. Why? It slapped back on my hand. If I tapped it like that, it doesn't hurt as bad. When I slap like that, I'm not going to, it hurts worse. Why? It hits back on me with whatever force I apply. Unless, of course, some breakage or motion happens, right? You didn't see motion on the part of the desk. Since it didn't budge, that's why. Now imagine there had been a balloon sitting here. I go, whop! Is the balloon able to push back with the equal reaction force? No. Hence the balloon goes flying, right? Or even a soccer ball sitting here, wham! Right? It goes flying because it's not able to push back on me. Does that make sense? With the same amount. So that's why it goes flying through the air. But if the object in question doesn't move, the ground, the wall, the pull-up bar, what have you, right? So anyway, action, reaction. You apply an action force, object doesn't move, the reaction force is equal in magnitude, opposite in direction. So we use a negative to indicate the opposite direction. Questions on Newton's third law? Okay. We'll stop there. And to give you a chance to practice some of the math from the second law of motion, homework for this evening. Homework for this evening is to read pages 115 to 118. Read pages 115 to 118. On page 128, answer questions 10, 11, 12, and 16. On page 128, answer questions 10, 11, 12, and 16. And also on page 129, you're going to do 3 problems that deal with Newton's second law. You're going to do problems 3, 5, and 8. Page 129, do problems 3, 5, and 8. And we'll take a look at that math in our next lesson, review over this as well, and then we'll move on to a couple more forces that help to explain motion. We referred to a couple of them already today. All right, when the bell rings, you'll be dismissed. Have a wonderful rest of your day.